Welcome to the third lecture of week 2 and which is on filtration. We are discussing filtration and we have already discussed this in lecture 1 and lecture 2, and here we will discuss filtration cycle and further we will solve a few examples based on filtration process. So, let us start this filtration cycle. Now, if you see the filtration cycle, how the filtration cycle is defined is the time required for filtration, time required for washing and time required for cleaning, dumping and reassembling of the system. So, that complete time is basically called as the filtration cycle. So, filtration cycle, that is T cycle, is defined as TF plus T wash plus T etc. So, T cycle is defined as TF plus T wash plus T etc. TF is the time required for filtration, T wash is the time required for washing the cake, that can be defined as volume of wash water divided by rate of washing, and T etc. is time for draining, filling, opening, dumping the cake and reassembling. Here we are considering the case the constant pressure with incompressible sludge, and we are assuming filter media resistance to be negligible. So, considering all these factors, we have the equation dt by dv equal to kpv, that is constant pressure and incompressible sludge. Kp we have defined like this as we have seen in the last lecture. So, once we integrate it, we can get the expression T equal to Kp V square by 2, which is equal to Tf, because this T, if we see, that will be the time associated with the filtration. So, this T value we can equate to Tf, that is time required for filtration. Now, here we can define X, which is nothing but the ratio of volume of wash water used to the final volume of filtrate collected. It means X is the factor which is which gives the ratio between volume of water required in washing divided by total volume collected during filtration process, and Y is the ratio of rate of washing to the final rate of filtration. So, this X and Y are basically relating the parameter associated with washing and parameter associated with filtration. So, time required for washing is T wash equal to X Vf by Y 1 by Kp Vf. Now, X Vf is the final volume of filtrate that is collected and into X, so that should be the volume of wash water, and similarly Y into 1 by Kp Vf. Now, if you see the filtration equation, when we consider dV by dt, that should be the rate of filtration. So, its value should be 1 by Kp V. So, that we have put over here, and Y is the ratio. So, this complete factor will give the rate of filtration. So, X by Y Kp Vf square. Now, T cycle is T cycle consists of Tf, T wash and T etc. Putting the value of Tf and putting the expression of Tf and T wash over here, we can get this expression as T cycle. Now, we have to optimize the cycle time, and the basis of this we have considered the total volume collected in 1 day, that is the basis. So, that volume which we have to collected, that we have to maximize to optimize the cycle time. So, number of cycles per day is 24 by T cycle. T cycle is the time associated with one cycle. So, 24 as we have to perform for single days. So, 24 divided by T cycle. So, daily collection of the filtrate, Vf is the volume of filtrate collected in a single cycle. So, 24 by T cycle, that should be the total number of cycles into Vf. So, that we have defined as V day. Now, putting here the expression of T cycle, this is the expression of V day, that is volume collected in a day. Now, if we consider this particular expression here, V day is a function of Vf. So differentiating V day with respect to Vf and putting equal to 0, we can get this equation, and when we solve this we can have expression of Vf which should be the optimum value, and its expression is like this. Further, after resolving this we can get this is the expression for Vf optimum. Now if we concentrate on this particular equation, that should be Kp by 2 Vf square plus x by y Kp Vf square minus t equal to 0. So we can take t etc. at this side, and if you see this expression, this we have derived for Tf and this we have derived for T wash. So Tf plus T wash is equal to T etc. So when we consider constant pressure with incompressible sludge, considering 0 media resistance, the optimum cycle for this, optimum cycle time for this is the time required for filtration as well as washing should be equal to the time required for dumping, cleaning, reassembling, etc. So here we have total optimum cycle time, which is Tf plus T wash plus T etc. This should be equal to T etc. So here we have optimum cycle time is 2 into T etc. So in this way we can define the filtration cycle and we can optimize the cycle time of filtration. So that is all about the theory part. Now from here onward we will discuss a few examples which are based on batch filtration process, so that you can understand whatever equations we have derived, how we can utilize this to calculate the different parameter associated with the filtration process. So here we have example 1. In this example, a plate and frame filter. Now what is this plate and frame filter, that we will discuss in subsequent lecture. So a plate and frame filter having 1.5 meter square surface area, where filtering is carried out at constant pressure. So you can see this is the constant pressure phenomena. In the feed, 10% solid having specific gravity 3 is mixed in the water. During filtration, incompressible cake is formed. So this is the case of constant pressure and incompressible cake. Now what we have to do over here is, in part A, compute the time required to wash the cake formed at the end of 90 minutes of filtering at the same pressure using 5 meter cube of wash water. So here we have to calculate the washing time, and in second part, if the time for dumping the cake and reassembling the press is 1 hour, what is the optimum cycle time and volume of filtrate collected per day? Wash water is used in the same proportion to the final filtrate as in part A. So here first of all we have to calculate the time required for washing, and then we have to optimize the filtration cycle. So as far as operating data is concerned, this is the this data we have obtained by batch filtration, where according to the time filtrate volume vary. So this is the data for batch filtration. So let's start the calculation of this. The filtration is carried out at constant pressure with incompressible cake. So final equation is for this case, as we have seen in the last lecture, is delta T by delta V equal to Kp V average plus B. So here we have to plot the graph between delta T and between delta T by delta V and V average. So first of all we will calculate this value. If you see the operating data for this, we are given time and volume. Time is we write in a seconds and volume is in meter cube. So we can calculate delta T over here, that is this time minus this time, and similarly this minus this, that is quite easy calculation. And here we have delta V, difference in the volume. So this minus this 1.99, further this minus this 1.56. In the similar line we can calculate other values of delta V. Now once we have the value of V and delta V, we can calculate V average. How that V average expression is, if you see, that is V plus delta V by 2. So here 6.1 plus 1.99 by 2, so that should be 7.095, and for other cases we can also calculate V average, and here we have delta T as well as delta V. Division of these two will give these value. Now we can draw the graph between delta T by delta V and V average. So once we draw the graph between delta T by delta V and V average, here the few points are available, and once we join these points we can get the straight line, and slope of this straight line will give the value of Kp, and that comes as 40 second per meter power 6. And when we see the intercept of this line, that its value is 40 second per meter cube. So governing equation becomes dt by dv equal to 40 V plus 40, because all value of Kp as well as value of B both are 40. So we can get the filtration equation dt by dv equal to 40 V plus 40. Now if we reverse this, if we reverse dv by dt, that should becomes the rate of filtration. So time of washing is to be predicted at the end of 90 minutes of filtration at the same pressure. So here what we have to do is whatever rate of filtration at the end of 90 minutes, the same rate we can consider as the rate of washing, because operation is carried out at same pressure. So here we have dv by dt f, because we have used the final rate, so that should be equal to 1 by 40 Vf plus 40. Vf is the volume, Vf is the final volume of filtrate collected at the end of 90 minutes. Now here integrating the equation, which the equation we have obtained is this, and when we integrate this for time, the time comes as 20 V square plus 40 V. So total filtration is carried out for 90 minutes, so that is 5400 second. So this 5400 second can be replaced over here, and whatever volume is collected at 5400 second, that should be the final volume of filtrate. So that we can obtain while putting 5400 as the value of T, and we solving this equation we can find Vf as 15.4621 meter cube. And final rate of filtration, as we have seen in the last slide, is dv by dt equal to 1 by 40 Vf plus 40. Now this Vf is the final volume of filtrate when we put its value, which is 15.4621 over here. We can get final rate of filtration, which should be equal to 0.00152 meter cube per second. And here you can understand that as per the problem, the rate of washing will depend on final rate of filtration. So rate of washing in this case should also be equal to 0.00152 meter cube per second. So we already know the rate of washing, we know the volume of wash water used, and that should be 5 meter cube. Therefore time required to wash the cake should be volume of wash water divided by rate of filtration. So that comes as 3292.42 second, that is 54.87 minutes. So here we have solved the first part of this. Now the ratio of volume of wash water to final filtrate volume, that is V wash by Vf. If you remember, this factor we have defined as x, so that factor comes as 0.3234. Now in part B we have to find the optimum cycle time, and cycle time, if you remember, we have defined as Tf plus T wash plus T etc. T etc. is given as 1 hour, that is 3600 seconds. Tf is time of filtration, that is 20 Vf square plus 40 Vf. T wash is volume of wash water by rate of washing. So T wash we can define as this is the volume of wash water and this is the rate of washing, as it is equal to final rate of filtration. After solving this, we can get 12.936 Vf square plus 12.936 Vf, that is the expression of T wash. So I know the expression of Tf and T wash. While putting all these expression in T cycle, here we can get the final expression of T cycle in terms of Vf. Now optimum cycle time, how we can calculate this? By maximize the daily output of the filtration process. So in that case, first of all we have to calculate number of cycles per day. So that should be 24 into 3600 divided by T cycle. T cycle is the time required for one cycle, and V day is equal to total volume collected in a day. So Vf is the total volume collected in single cycle, so that we should multiply it with total number of cycles. So 24 into 300 into Vf divided by T cycle, and further while putting all values of all known values, we can get V day equal to 86400 Vf by this expression, that is the expression of T cycle. Now to maximize this V day, we will differentiate with respect to Vf and equate it to 0. So Vf optimum is 10.455 meter cube and T cycle optimum cycle time is this much. So while putting the value of Vf over here, we can get 7753.46 second, that is 2.154 hours. So that is total cycle time which is already optimized. So that is optimum cycle time. So in this way we can calculate, we can optimize the cycle time, we can calculate total time required for washing. Now here we have second example. In this example, a filter handles a sludge that consists of 70 kg of solid per 1000 kg water and forms a compressible cake. So here you see the cake is compressible. The experimental data generated through filter of area 0.65 meter square is shown in following table. Estimate the filter media resistance and compressibility coefficient of the cake. So what we have to calculate over here is RM value as well as S value. The experimental data of constant pressure filtration is already given. Now if you see this table, here we have three values of pressure, but for one pressure whole filtration process will be carried out, and then the pressure value is changed and then whole filtration process will be carried out. So here we have, though here we have three different value of pressure, but this is constant pressure phenomena. Now if you see this, the what type of case it is constant pressure with compressible cake, that is the case. And for compressibility and for alpha value, we can use Sperry correlation, that is alpha naught pressure drop power S. So in this example, RM and S are to be calculated. So this is the expression for constant pressure and compressible sludge, Kp dash V average plus B dt del T by del V. So here we have the equation for constant pressure and compressible sludge, and that is delta T by delta V equal to Kp dash V average plus B. Kp dash we have defined like this, where we can found the value of S and value of RM can be found by value of B. So here we have to find delta T by delta V and V average. So delta T for all different pressures we can find, as we have discussed in the last example. Delta V we can calculate because volume corresponding to time is known. So delta V3 we can calculate, and further V average we can calculate, as we have seen in the last example. And similarly delta T by delta V can be calculated for different pressures. Now what we have to do, we have to draw the graph between delta T by delta V and V average. So you see here we have for three different pressure, three lines are there. So here we have three different pressures and therefore three different curves are appearing in this graph. It is drawn between delta t by delta v and v average. While drawing the line for each case, we can find different slopes as well as different b values. So, for delta p, that is 10, if you consider this 10, so this is the graph, it has Kp dash, Kp dash means it has the slope like this, and b value we have like this. So, if you see all these three graphs, we can calculate, if we observe the slope, it has the highest slope, then this and then this, and similarly values are appearing in this table. B we can also calculate from the intercept, and those are available over here. Once we know the value of B, we can calculate RM value, because we know other factors, other parameters. So, RM can be calculated directly from the B value. So, as we have 3 value, 3 RM value we will obtain, and average of these 3 RM value will give the final value of RM, that is filter media resistance, and that is obtained as 2.33 into 10 to the power 8 meter minus 1. Now, further we will use the data of pressure drop, which we have seen from the last curve, pressure drop and Kp dash. So, here we have 3 pressure drops value and 3 Kp dash values. The Kp dash expression, when we take log of this is the final expression, and here Kp dash will be dependent on pressure drop. So, Kp dash versus pressure drop we can draw. Here we have 3 points, so 3 points are appearing over here. Now, you see here, if we consider this particular section as well as this section, this is logarithmic axis. If we consider this y axis as well as x axis, these are nothing but the logarithmic axis. Now, for these 3 points, when we draw the line will be like this, and slope of this line would be negative. So, that is minus 1 minus s. So, if we consider the value of this, that should be equal to 1 minus s, which is 0.889. So, from here we can calculate value of s, which comes as 0.111. So, in this way we can calculate factors which are associated with the filter media as well as compressible cake. Now, here I am considering third example, where a sludge filtered in a washing plate and frame filter press is of such nature that filtration equation is V square equal to KT, where V is the volume of filtrate obtained in time t when the pressure is constant. 40 meter cube of filtrate is produced in 10 hours and 4 meter cube of washed water is used for washing at the end of filtration. So, what we have to calculate is the washing time if washing rate is 1/3 of the filtration rate, and secondly, if the filtering surface is double, remaining other conditions constant, how long it take to produce 25 meter cube of filtrate. So, let us start with part 1. Filtration equation we have given like this, V square equal to KT. When we differentiate it, we can found dV by dt is equal to K by 2V, which is nothing but the rate of filtration. Now, in part A, at time t equal to 10 hours, volume is given as 40 meter cube. So, when we put these values over here, we can find value of constant K, that should be V square by T. So, the value comes as 160 meter 6 by hour, and rate of filtration should be K by 2V, so that we can found as 2 meter cube per hour. So, washing rate, if you see, washing rate is basically considered as 1/3 of the rate of filtration. So, 2 meter cube per hour is the rate of filtration. So, rate of washing should be 0.667, 1/3 of that. Therefore, washing time should be 4, which is the total volume of wash water we are using, divided by 0.667. So, 6 hours should be the washing time. Now, in part B, as it is constant pressure phenomena, it is denoted as expression should be dt by dV equal to Kpv plus B, where Kp is defined like this. In the present problem, dt by dV should be equal to 2V by K. Now when we compare this equation with the above equation, we can correlate that K is proportional to area square. So when we double the area, the revised coefficient should be 4 times than the previous one. So revised coefficient value should be 4 into 160, because 160 is the previous coefficient value. So final K dash should be 640 meter 6 per hour. So time to produce 25 meter cube of filtrate, that should be V square by K dash. If we see the final filtration equation, volume we can put as 25 meter cube. So solving this, we can get 0.976 hour, that is 58.6 minutes. Now here, if we would like to see what should be the time required to generate 40 meter cube of filtrate when filtered area, when area of filter media is doubled. So in that case, because K is proportional to area square, so when we double the area, K dash should be 4 times. So when we for 40 meter, so for generation of 40 meter cube of filtration, it will require 2.5 hours instead of 10 hours. So here we have seen 3 different examples to make you understand how the governing equation will be used to calculate different factors associated with the filtration process. So here we have the summary of the lecture, and you should keep in mind that this summary is for lecture 1, 2 and 3. So in this series of 3 lectures, filtration operation along with its types and applications is discussed. Design equation for batch filtration is derived, and different cases related to these are identified and discussed. And finally, a few examples on filtration operation are discussed. Here we have the references through which you can study about filtration in detail, and that's all for now. Thank you.